Okay, guys, let me try the light bulb thing again. So let's back up and let's talk about what it means for something to be ohmic. So V versus I looks like that, where the slope is the resistance, right? So an ohmic object means that it has a constant resistance. If something is non-ohmic, then it might look like that, okay? So because the slope is resistance, obviously the slope here, we're talking about tangents, right? So you can see here, the resistance is increasing, okay? So if you remember what resistance is, it's, right, rho L over A, where resistivity has to do with that material. Well, what you hopefully see here is that resistivity can be a function of other things, and most often it's temperature. So if you have a light bulb, right, so this is not constant resistance. So if you have a light bulb and you get a certain current, when applied a certain voltage, like here, down here, this is called the cold resistance, and then up here is the hot resistance. So you can see that R increases as temperature increases, and hopefully that makes some sense. If you think about what the electrons are doing in the in the wire-ish. I say wire, but here I'm talking about like a filament of a light bulb. If you increase the temperature, you're going to get more jiggliness, and so you could imagine that would make the electrons be able to flow differently, right? And it's not necessarily obvious if it's easier or not, but you can at least imagine how that temperature could at least affect that resistance. And that's actually what you see, is that the resistance of a light bulb at the beginning, when it's still cold, is that slope, and then when it gets hot, so hot that it glows, right? Then it's actually a different resistance. So those are real light bulbs. When we talk about light bulbs in physics, we might have a circuit, and it'll look like this. So that's how we draw light bulbs. And we talk about, a light bulb having a resistance, right? And so if they're identical light bulbs, so now I'm talking about like living in physics land, right? In physics class land, I should say. So identical light bulbs means they have the same R, okay? A lot of times you talk about power with a light bulb, right? So hopefully, right, that light bulbs are things like, 100 watts or 60 watts, right? These are powers, because that's a watt. So what does that actually mean? So when you think of a 100-watt light bulb versus a 60-watt light bulb, hopefully you realize that the 100-watt light bulb is brighter, okay? So oftentimes in questions, they'll ask about the brightness. And the brightness means power, okay? If you're comparing two identical light bulbs, and so that means that they have the same R, okay? If they say, which is brighter, right? of these two light bulbs, then what you really want to look at is the current. Determines the brightness if R is the same. Okay, so that's a really, really common kinds of question. Is they give you a setup, and then they say, they ask you about brightness of light bulbs. So if they're all the identical light bulb, then you are just asked, right? So the brighter one is the one with more current. Okay. You might also be curious how does a 100-watt versus a 60-watt light bulb, how do they compare? Right, they're going to be different, right? Different resistances. And so the question is which one has a bigger resistance? So I guess one of the things you need to know is how do they actually rate these? That power of 100 watts is determined with a certain voltage applied, and that voltage is what we get in our houses, is 120 volts. So in that case, if we looked at power as V squared over R, right, 100-watt light bulb, right, you can calculate the resistance of a 100-watt light bulb, and you can calculate the resistance of a 60-watt light bulb. And hopefully you see that the resistance is less for a brighter light bulb. Okay? You can see that with the math, but you could also probably intuit that a little bit, that if the R is less, you're going to get more of a current through it, and the current's probably going to translate into brightness somehow. So hopefully that clears up what I basically totally botched in class with the light bulbs. Okay, so moving on. All right, moving on. We'll just sort of redo the series and parallel circuits, because I think it's useful. All right, so boom, boom, boom. All right, what do we got? Hey, in class I used, 12 volts and 2 ohms and 4 ohms. How about I use 18 volts, and how about 3 ohms and 9 ohms? Ooh, fun. Okay, so you are this battery. You look out to the circuit and you say, what is your equivalent resistance? And you say, aha, you are in series, right? You see this current and it goes through the 3 ohm, through the 9 ohm, same current, so you know that those are in series. And so this is how it goes for series. So our equivalent resistance is 3 plus 9, so it's 12 ohms. So what does this battery pump out? It's 18 volts divided by 12 ohms, which is 1.5 amps. Okay, so that is what's pumping through both, right? The 3 ohm and the 9 ohm have, oopsies, just kidding, 1.5 amps. Amps? Really? Amps? Through them. So, question is, what's the voltage drop across them? So, here's 18, here's 18. That's 0, diddle, 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 0. Okay, so there's going to be a voltage drop across here that you can measure, and a voltage drop across here that you can measure. Okay, and the way you get that, the voltage drop over the 3 ohm, is the current through the 3 ohm times the resistance of the 3 ohm. And I know that's kind of seems like overkill with all those subscripts, but I think it's useful to remember what those things mean. When we say V equals IR, we're talking about the voltage drop across a certain thing with that current through that thing and the resistance of that thing. So the voltage drop across the 3 ohm is 1.5 amps times 3 ohms, which is 4.5 volts. Now, so that means, so we just calculated that as 4.5 volts. So there are 2 ways that you could figure out the voltage across the 9 ohm. Can you think of them? One way is that you know that if, here let's pick black again, if this right here is 18 and there's a 4.5 volt drop, then you know that the potential here is 18 minus 4.5. So right here is 13.5 volts. So what's the voltage drop across the 9 ohm? Well, it's 13.5 minus 0. So the voltage across the 9 ohm should be 13.5 volts. 13.5 volts plus 4.5, 18. Good. But it should also be, you could also use, 9 ohm, use Ohm's law, right? So the voltage across the 9 ohm should be 1.5 volts times 9. And guess what that is? That's 13.5 volts. So, this is, I'm glad we're doing this because there are a lot of different ways of finding out the same information. And that's good, but it also can be very frustrating. If you make a mistake, because obviously right now these are really easy circuits with 2 resistors in series and that's it. When we get into more complicated circuits, you are going to have lots of different ways of approaching it and checking, right? There were 2 ways for me to figure out that 13.5 volts, and that's going to happen a lot. If you make a mistake, then all of a sudden things won't be consistent, right? I figured out 13.5 volts one way, and then if I tried the other way, then maybe it doesn't work out. And so you've made a mistake somewhere. It can get super, super frustrating when that happens. If you are doing a super complicated circuit and that happens, my best advice to you is throw away your piece of paper and start from scratch, because just trust me from experience. All right, let's do parallel now. So let's do this. Let's do our 18 volts again. So here's 0, and let's do a 3 ohm and a 9 ohm. So the battery looks and says, what is your equivalent resistance, my dear? And here it goes. So it's 1/3 plus 1/9 is 1 over our equivalent. So what is that? 9. And then that's 3 plus 1. So that's 4/9. So our equivalent is 9/4 of an ohm. Okay. FYI, when it's numbers like this with fractions, very often it's easier to leave it in fraction, like a 9/4, because you're going to be multiplying it by other things, and a lot of times those factors show up and easily cancel. So what is the current that's going to get popped out of the battery? Okay, 18 volts, and then here's 9/4 of an ohm. So as I was just saying, so 18 divided by 9 is 2, and 2 times 4 is 8. So that is 8 amps is what comes out of here. 8 amps. So those 8 amps come here, and they get to this fork in the road, and you have a 3 ohm guy, and you have a 9 ohm guy, and this little charge that gets here says, where should I go? And the fact is that the current through the 3 ohm versus the current through the 9 ohm, they're not going to just split evenly, because one is much more attractive than the other. The 3 ohm is a much nicer path, so more charges will choose that. Okay, quick. Some people really hate when you anthropomorphize in physics, but I think it's useful, but hopefully you understand that it's not actually the thing choosing like this. It is a useful tool. So the 3 ohm path will have 3 times the 9 ohm path's current. Okay, it is 3 times more, if you want, more likely for that charge to go through there. All right, it is more attractive. So there's a couple of different ways to figure out the actual amount of charge, or the amount of current. So you could say they have the same voltage across them, right? So V across 3 is equal to the V across the 9. So that's I going through the 3 times the R of the 3, and that's I of the 9, R of the 9. Okay, so when you see this I3, if this is 3 ohms, this is I9, and that's 9 ohms. Now you can see why I just was able to say I3 was 3 times I9. Okay, but what else is true? I3 plus I9 has to equal the total current coming in, which is 8 amps. Okay, so we can just plug that in. So I3 is 3 I9 plus I9 equals 8. I'm just going to drop the amp just so we can do it easier. So it's 4 I9 is 8. So the current going through the 9 ohm is 2 amps. How can we figure out the current going through the 3 ohm? Well, there's 2 ways to do it, right? If the total is 8 amps and this is 2 amps, then I3 must be 6 amps. And you can see that it's 3 times. It's 3 times the other one. Okay, so again, there's lots of different ways of playing with these equations. You could have also done, like you knew that it was 18 volts across here. So you could have written 18 volts is I3 times R3, right? And so this was 18 was 3, right? That was the resistance, times I3. So I3 was 18 divided by 3, 6 amps, right? You could have done this with 18 volts is I9 times R9, and then it would have been 18 volts divided by 2 amps is I3. So hopefully what you have seen here is that you can get these answers a lot of different ways, and with these problems that we're going to do, you are going to want to think about it in lots of different ways, because depending on what information you have or what information they're looking for, some of them will be more useful than others. So I encourage you to try a lot of those. Before I leave you with this, so I want to show you this other sort of next step of the setup. So let's say that's 18 volts, let's say that's 2 ohms, 3 ohms, 9 ohms. So when we're trying to figure out the equivalent resistance, look at that first. The equivalent resistance of that, which we just did on the previous slide, was, here, let me see if I can make this color coordinated. It was 9/4. an ohm, okay? And that was 2 amps. Try that again, 2 ohms. And then you can take this stuff is now in series, and so it's going to be 2 plus 9/4 ohm is going to be that. Okay, wow, I've kind of gone off the deep end here, because I feel like this video's already gone too long. So the way to get the current through that the battery gives out is that E divided by the R equivalent, okay? That's the current that goes out of the battery. So it's the current that goes through the 2 ohm, and then when it gets to the 3 and the 9, then it does that, 3 times the current goes through the 3 ohm, then the 9 ohm. Okay, and that 3 again is because the reason 3 times the current goes through the 3 ohm, then the 9 ohm is because 9 is 3 times that 3 ohm. That's the factor, right? So just to make that super clear, if this is R and this is 2R, then the currents that go through here, this, if this is a current I, then this will be I over 2. Okay, so half the current will go through the 2R and then through the R. And then what's this total current that's coming in here? That's I plus one half I. So that's 3/2 I. So a lot of times you'll see this as like, ooh, what if 3 amps comes in here? And here's an R and here's a 2R. You know that they have to add up to 3 and that there's, twice the current that goes through R. So 2 amps is going to go there, 1 amp is going to go there. So it ends up being a lot of sort of math games like that. All right, I hope this helped. All right, bye.